Hi everyone. In this lesson we will continue with the Bayesian decision theorem in artificial intelligence lesson. Okay, and so we will have title as the Bayesian decision theorem. Okay, but in order to understand the Bayesian decision theorem, we need to know about how we can analyze the probability in terms of the what, the sum coefficients, especially for the what, the conditional probability, prior probability, or the mean and standard variation of the what are data. Okay, the probability is one of the basic fundamental concepts to represent any events that happen for a given condition. Okay, given condition. So in a mathematical perspective, it's basically a transformation a line into area form, which is shown as the probability rate of an event. Okay, in order to understand the probability distribution, we need to analyze the subset classes. Firstly, we should create the what, the sum I mentioned in here, like this one, and so these are the sample numbers. For example, we assign this axis as x, and this is the number of samples. Okay, and so if we have this line in here, and then maybe we have the 80 data in here, like this one. Okay, and also if we have this nomination, and then maybe we have the sum distribution in here for a given data, like this one. And so this is started with the 120 values. Okay, and after that maybe we can assign the 300 data in here. Firstly, if we analyze this picture, and then we can say that this is maybe one class C1, and this is the another class C2, by observing the data just only. Okay, so in order to create the conditions in here, like this one, firstly we should say that for a given any x value, x may be a measurement of a sensor or the actuator or the any variable which is used in the engineering applications, and then we can say that it is presence or the existence of the data, which means that if we have any measurement in here, and then we can say that this data is exist in the for a given space. Okay, and then we can create the probability rates of the probability of these terms in order to in order to find out its mechanism in the probabilistic or the mathematical way. Okay, so we can say that this is another term in here for the classes. We can create the following form. If we have the C1 and C2, we can create a two subset variable in here, like this one, and so this is called the C1 and C2, and we have the sum intersection points of the area, which means that this is equals to the 80 to 120. Okay, and so this may be 0, and this is goes to 300. But in this data we can create the probability for a given x, and so this x contains the class 1 and class 2. Okay, and so if we have or there exists any data related to the x value, and then we can build the C1 and C2 classes in here, but with with some properties of the conditions, okay? And also we should give that the P C1 combination C2 is equals to the what? The probability C1 plus probability C2 minus C1 intersection C2, okay? And the event of the X is entirely depends of the any other things, and which means that we can assume that the Px, or the probability rate of the happening rate of these terms, must be equals to the what? The 1. But we can assign the what? The different values in here, because if we have any measurements for a time, for example, if we have the 10 seconds period in here, like this one, we have events in the t and, for example, 2 and 5, okay? And so maybe we obtain the x data in here, but the total process contains what? The 10 seconds periods, okay? And so this is the 3, and so the px in this case 0.3, okay? Because the entire process contains the 10 seconds, but we have only utilized 3 seconds values, okay? And it's the present values, or the presence values of these terms can be conditioned or obtained by using these informations, okay? And so as a result, we can say that the whole probability, or the whole process, should be conditioned by using any other terms, okay? And so we can say that we have some general pattern in order to analyze this probability, which means that we have the what? The one, the conditional probability. We can say that. Okay. Now we have two subsets for a given x, okay? And so how can we connect these two cases related to each other, okay? And so firstly we need to create the what? The some Euler diagrams, or the conditional probability. Of a or any x for a given C1 and C2. In order to analyze it, we should drive the what? The Euler diagram of any cases in here, okay? Which means that we can define, for example, this instead of C1 we can create the B1 values in here and B2 subset in here and B3, and can build the what? The A classes in here, like this one, A, and we should also give the total present values, or the happening probability, as a what? The omega values, okay? And so if there is omega, and then we can see that we may A feature, or the A process, or the B1 process, or the B2 process, or the B3 process, okay? And so we can assign the what? The B1, the happening rate, as the what? The 0.1, okay? Or this is equal to 0.12 and 0.04, okay? And so maybe this is the 0.1 and 0.34, or we can say that 0.3, okay? So these are the probability rate of the events for a given what? These omega values, okay? And so we should say that the total probability can be assigned as the what? The P omega is equal to the 1, okay? If this present, and then we can say that we build the A class B1, B2, or B3, okay? But the probability of A and the given omega, then we can say that the PA is equal to what? The 0.3 plus and 0.1 plus 0.2. Okay, because we have these combinations in here. I'm sorry, this is the 0.12. Okay, and so this is equal to the what? The 0.52. Okay, because if there is any data related to what the omega values, and then we can say that the A has a probability rate of what? The 0.1, 0.3 and 0.12 or 12. Okay, or we can create the what? The another formulation for the what? The, for example, if we have the probability of to what? The B1 given omega values can be calculated with what? The B1 is equal to the what? The 0.1. Okay, and so this term B1 given omega values can be written as the what? The P B1 for a given omega values is equal to the what? The 0.1. This is the conditional probability, because if we have, or if we talk about the what? The B1 probability, and then we must say that this omega should be exist in this case, and so we can analyze the B1 probability for only the condition is satisfied that is the what? The omega is present in here. Okay, and so we should, or we can also say that this P B1 omega values can be assigned with what? The total probability in here, like this one, because it's the rate of the what? It's contains the whole the probability of the whole process. For example, A, B, B1, B2, B3, but we should only process the what? B intersection points of the what? The omega values. Okay, or we can write that in here P A B2 means that P A intersection B2 divided by B2, right? And so A contains the whole the B1 data, which means that, or B2 data. Okay, and so if we have the B2 data in A, and so this still represent what? 0.12. Okay, and so this must be written in here like this one, because it's the intersection points, but the B2 probability is equals to the what? The 0.12 plus 0.04. Okay, and so this equals to what? 0.75. Okay, this is the conditional probability for a given any event in here, and so we can calculate it. It's by, or the with respect to the what? For a given condition. We must always use this notion in order to what? To create the R representations. Okay, and so we need to return to the what? To other diagrams in here. Now return the graph of X, and so we can write that this term X, and we have the sum data with this distribution, and then we can increase data, and we have the sum another data in here, but it contains the what? This whole data represents the X, and we have the 400 data in here like this one, and we have the 120, and we have the 8 value, and this is the 0 values. Okay, and so how can I convert these terms into the Euler diagrams? In Euler diagrams, we should say that the whole representation, whole the probability conditioned with the what? The X, and so this rectangle represents the X probability. But we should define the what the C1 in here and C2 in here, but we can define the intersection point. What we don't need to do that. Okay, and so this is the what the R probability rate in here. And so how can we create the what the C1 probability or the prior probability in here? Or how can we create the what to calculate the C2 probability in here? And so we need to talk about the prior probability at this case. Okay? Then the second condition or the second topic is related to what the prior probability. How can we calculate the probability of the what the C1 and C2? The prior probability means that if there is no condition or any effect on this data, and so how can we create the initial guess of this C1 probability for a given X? Okay, and so I just simply create this P C1 values as the we have the total number of the 400 data which is given in here. Our numbers, this represents what the total number of the X is happening in here. And then we can say that we have the 80 values 0. Okay, and so this is equal to 1 divided by 5. Okay, or we can create the PC2 which is given in here like this one, 122 400s, and then we can say that we have this much data which is given in here in the C2 class, and then we can say these terms, and so the R probability is equals to what the 14 divided by 20. Okay, and so we can say that this is the 0.2 and this is the 0.7, and we can say that the 0.2 and 0.7 is given in here, and so the 0.1 or 10% of the probability which is given in the unstable range of these terms. Neither C1 or C2 is contained in this region. Okay, and so from this information, how can we do the R prior probability? The prior probability can be calculated with the number of classes points in here, and we should divide it with the total number of samples. But this is the guess of the R application. Maybe it's different from the another one. Okay, and so this information cannot be selected by the user, but the estimation of the probability is affected by these choices. Okay, and so you need to build this prior probability in order to create the Euler diagram of these forms by using this one. Okay, so these are the initial guess or the initial probability rate for the C1 and C2. And so what happens if I choose or if I add the C3 class in here? For example, this is the C3, C1 and C2, and so we can draw the circle in here, and C3 can be assigned in here. Just simple as that. Okay, so in the third topic we need to talk about the likelihood rate, likelihood probability. Okay, likelihood probability is some kind of conditional probability with the assumption of the some conditions. It's kind of conditional probability. But with the first assumption is that assume that each class follows the normal distributions. Okay? Assume that each class which we defined in here, for example, tall and short for the length of the human, okay? Tall, short, maybe x is the dimension of the humans, okay? Follows normal distribution, which means that we have the one mean and one standard deviation values, at least in this nomination. And the second assumption is that the estimation or the estimate, the model with the what, with mean and standard deviation, which is create the what are normal distributions. Okay? And so, how can we calculate this likelihood? Calculating likelihood can be given by the p x for a given c1, which means that if we have the c1 class values, and then we can control the how much data can be contained in this class. Okay? And so how can we do that? X intersection c1, and we can say that c1. Okay? And so for the graph we can say that the whole c1 is intersects with the x value, and 0.2 can be given in here. Okay? And so c1 probability is 0.2, and we can say that it's the 1. But these values are trained data. It's a present data. Okay? Just remember that. Or we can say that PC2 in here, pay x c2 divided by c2. Okay? And so this is equal to what? 0.7, 0.7. It's equal to the 1. But this is the trained condition, which we have it in these conditions and in this status. Okay? And so how can we reformulate these nominations with the new x data using these forms? And so we need to propose some other functions, which is written in the red formats in here, like this one. For example, if we have this p x c1, we can say that we can create normal distribution formulation in here, like this one. 2 pi times standard deviation 1 square exponential terms with the minus x mu 1 divided by 2 times sigma 1 square. Square can be given here, especially for the c2, same nominations in here, like this one, 2, 2 and 2. The same formulation is given in here. Okay? This is called the likelihood function. Likelihood. How much our representation is similar with with the normal distributions. Okay? And so if we have any present x data, and so we can put either the c1 class or either the c2. But in the c1 class we know that this class must be represented by the mean and standard deviation formulation. To build the probability rates or the probability conditions, which is the summation of these terms is equal to the 1. This is the integral of the area of these terms must be equal to the 1, just like this one. Okay? This must be satisfied. So how can we use this likelihood in order to build our probability rate? For example, just now we should say that this information can be utilized with the Bayes theorem, or building this Bayes theorem. This is the theoretical foundation of this theorem. Because let's turn into the what, the Euler diagram, which means that we have the what, the x and c1 and c2 is given in here, and then we can say that the px c1 equals to the what, the px intersection c1 divided by c1, or we can say that p c1 x is equals to the what, p c1 intersection x divided by px. And so these two intersection points are equals to each other. Okay, and so if we rewrite the whole equations like this one, pay x c1 is equal to the pay c1 intersection x, which is equal to the what, pay x c1 times p c1, and in the other terms, these terms should be multiplied with each other. And after that, if we say that this is true, and it must be, and then we can say that p c1 x must be equal to the what, pay x c1 times p c1 and pay x. Okay, and so this is the probability of the px, this probability of the pc1. And so what's this? This is the probability of the x for a given c1, but in this case this is the class c1 probability for a given x. Okay, and so this is called the likelihood. This is the prior probability px and the other term, but this is called the what, the posterior probability. Okay, and so if we have the any distribution for a given x and c1, and we can build the what, the likelihood function like this one, and then this likelihood function for a new data, and then we can assign or find the posterior probability or the happening rate of the what, the new x data, which is given in the c1 class. And so this is also a classification problem. By using the what? By using the likelihood function or this function. Okay, and so if we have the any model in here like this one, mu and standard deviation values, and so we can utilize the prior probability in here, and then we can reach the what, the posterior probability for a new x data in order to create this model. This is called the Bayes theorem. Bayes theorem is just like the what, so we kind of the Pythagorean theorem in the linear algebra or the math. This is the foundation of the what, the connection between the what, the input and the output, or the prior to posterior probability for a given any model. Okay, this is so important, and the eligible techniques to what, to build the R nominations or the R probability distributions for the what, the classification problems. Okay, that's all. So how can we do that? So we need to talk about these terms in here, and then we should say that also we need to give what, the Naïve Bayes classifier, because it's the basic foundations of the what, the R probability rate of the what, these terms. And then if we use this theorem in here like this one, and then we can classify the data or the data representation by modeling with the what, the likelihood ratios in here. Okay, so we should say that we have what, this head title, Naïve or simple Bayes classifier topic in here. Okay. And so up to now we have talked about the bias rule and its implementation of the probability using the proposed model have been discussed in order to show the power of probability, because if we have the likelihood function, it's the model function, and then we can use the prior probability to obtain the final probability or the posterior probability of the what our condition or the classification performance, which means that if we have the NC1 class and then we can test that the new X data can be contained or not. Okay, and so but we introduced a new concept to classify data into specific classes, which call the Naïve bias classifier. Naïve means just the simple bias classifier. Okay, and so in order to write this term, we should first say or discuss about that the Naïve. It's a strong assumption. Because if we have the any data, we just model the R system for a given the mu and standard deviation values, or the multidimensional data. We have the 2D data, we have the mu or the mean vector and the covariance matrices. Okay, and so we can condition all the data is that the Naïve simply accept that the whole data is represented by using only the C1 class or the C2 class. This is a strong assumption, because there is another way to build the any class in here. Okay, we cannot add the C3 class or C4 class, or we can add it, but if we add that, we just simply classify to the 4 classes or the 5 or the 6, but any other class cannot be included in these terms in here. Okay, just simple is that if your neural network is running, and then you can run this neural network for the detection of the face or not, and so this neural network only sees that this is the face or not. They cannot discriminate to the arm or body or the football tops. Okay, and so how can we create these terms in here? First, the bias theorem is expressed with these terms P C X is equals to the P X C times P C and P X. Okay, and the assumption is that the features are conditionally independent for a given class. Which means that this X value either is contained in the C1 or C2 or C3 or C4. Okay, and we must say that the prior probabilities are known, because if we have this nomination or the bias rule, and then we need to know about the values of the Px or Pc. Okay, and so let's say the x1 and x2 are the features and the c1 and c2 are classes. Okay, then we can say that in this nomination, let's say x1, x2 features, we have two-dimensional data in here, and then c1 and c2 are classes. Our conditions are that. Okay, and so the problem formulation can be given by with the pc1, x1 and x2, which means that the interpretation of this probability is that for a given x1 and x2, it is the probability of the C1. Okay. And so this new data, x1 and x2, is stored within in the what, the C1 or not. This is the probability of these terms. Okay. And then we can say that if the R features are conditionally independent for each class, and then we can write that the P x1 C1, this is the probability of the what, the C1 for a given C1, the x1 is contained or not. Okay. And so we can also write that the P x2 C2, because it's are the independent vector, and then we can multiply these two probability in here. And also we should give the what, the C1 and pay x1 times P x2. These are conditions. And the same rule is applied with what, the C2, x1 and x2. Okay. And so we can write that this is the terms of the what, the P x1 C1 times P x2 and C2 probability, because it's the rate of the what, the class, it's normal distribution. x1 is contained in here, C2 x2. If for a given the C2, x2 is within the C2 or not, this is the indication of these terms, and P C2 should be given in here, and then P x1 times P x2 prior probability must be given in here. Okay. This is the Naïve bias classifier. And so how can we create the what, the pxi and cj values in here? Firstly, we need to write that this is the normal distribution, and then 2 pi sigma j square, because j is indicating what, the class values, and multiplication with what, the exponential terms of the what, minus xi minus mu j square 2 times sigma j square. Okay. These are the what, the basic Naïve class formulation. And so we need to build this two model in our Python implementation code, and then we can check the whole the x1 and x8 data into the what, the probability rates of the what, the C1 and C2. And then we can detect that the C1, x1 and x2 is contained either in the C1 or C2. Okay. If the C1 probability, the first probability, is greater than these terms, and then we can say that this is C1 class, or this P C2 for a given x1 and x2 is greater than the what, the P C1 for a given x1 and x2, and then we can say that this is the class 2 data. Okay. And so in the next lesson we will talk about it.